If you thought that relativity is only relevant at velocities close to the speed of light, think again. Relativistic effects can be absolutely crucial at velocities way slower than the speed of a snail. And it has nothing to do with some sophisticated quantum effects. I'm talking about a mysterious force discovered already in the 19th century that remained one of the greatest unsolved problems in physics for nearly 30 years. Until...
Hello and welcome to the 6th episode of my online course on special relativity. My name is Andrzej Dragan. I'm a professor of theoretical physics at University of Warsaw and National University of Singapore. And today, we just cut to the chase.
So here's a formula that you have seen many times. It's a magnetic force known as a Lorentz Force, acting on the electric charge Q, moving with velocity v, in the external magnetic field B. And this looks pretty innocent until you ask the question, what is that velocity v? Because after all, you can always pick a frame of reference in which that velocity vanishes. And then what? Will the magnetic force also vanish? So this is the problem that made physicists scratch their heads for nearly 30 years. And Albert Einstein was the first guy to solve it. And to understand what's the problem here, let us consider an example in which the magnetic field is generated by a piece of metallic wire conducting an electric current. Such a current is essentially a stream of electrons moving in one direction, and that stream of electrons generates the magnetic field circulating around the cable. So if you place additional electron outside of the wire that is also moving with the other electrons, then the magnetic field will generate a magnetic force attracting the electron towards the wire. So this story is pretty straightforward until we ask the question, what happens in a frame co-moving with all the electrons? Because in that frame, the magnetic force has to vanish simply because the electrons are not moving anymore. And it seems that we have inconsistency with the principle of relativity because in one frame, the electron is attracted towards the wire and the other it's not. So before we continue, we have to ask what happens to the electric current in the new frame of reference. And to answer that, we have to realize that the wire contains not only the electrons, but also positively charged ions that in the first frame of reference are simply at rest and compensate the total electric charge of the wire. But in the new frame of reference, the moving one, the electrons are at rest, but the ions are moving in the opposite direction and they generate the same electric current and also the same external magnetic field. However, in this case, the outside electron will not feel any magnetic force simply because it is not moving.
So the big surprise here is that the only way to solve this problem is by using relativity.
And it's really hard to believe because the motion of the electrons inside the wire is really slow. A typical velocity of such electrons is of the order of centimeters per minute. Even snails move faster. So it's really hard to believe that relativity has anything to do with this. And it does. And the crucial effect to take into account here is the Lorentz contraction. All the electric charges, when they start to move, they approach each other. So when we change the frame of reference into the one in which the positively charged ions move, those ions will approach each other. And therefore the concentration of the positive charge will increase. And conversely, since all the electrons stop moving in this frame of reference, they will move apart from each other and the concentration of the negative charge will drop. So in this frame of reference, the wire is not electrically neutral anymore. It has some positive charge density, and that charge density will create electric field outside of the wire, and that electric field will generate electric force, attracting the external electron towards the wire. So you see, what we need to take into account is not just magnetic Lorentz force, but also its electric component that is inseparable from the total electromagnetic force. So qualitatively, everything starts to make sense. we have an attractive force acting in both frames of reference. But the question is whether the value of that force is identical in both frames of reference. And this is a very standard problem in the theory of electromagnetism. We can easily compute the magnetic field outside of the wire at a distance r, and as a result we find that the magnetic field is proportional to the current intensity and inversely proportional to the distance from the wire. And here the mu0 constant is so-called magnetic permeability of the vacuum. We can also re-express the current intensity as the product of the electron concentration that we'll denote with rho minus, electronic charge E, velocity of electrons V, and the cross-section area of the wire S. And we can use all that to compute the magnetic force given by the following expression. In order to compute the electric force and electric field outside of the wire, we first find that the concentration of the electrons is reduced exactly by the Lorentz factor, and the concentration of positively charged ions increases by the same factor. But before we declare what is the charge density of the wire, we have to answer one more question. What happens to the total electric charge of a single electron when it moves?
So if I grab a piece of metal and heat it up, then I am democratically distributing some kinetic energy among all of its particles. And this way the light electrons gain much more speed than heavy ions. And therefore, if there was any dependence of the electric charge of those particles on their velocity, then by heating this object up, I would immediately charge it electrically. And no such effect has ever been observed, which can only indicate that the total charge of a single electron has to be completely independent on its velocity.
So the total charge density of the wire is a combination of the positive charges and the negative charges, and the resulting expression depends on the velocity of the charges in the following way. So we can now compute the electric field at the distance r from the wire, and here is the result, and in this result epsilon 0 is the so-called vacuum permittivity. So we are now ready to compute the electric force acting on the charge in the second frame of reference, and compare it with the magnetic force from the first frame. And the results do not look identical. There is a difference. In the first formula we have mu0, but in the second one there is epsilon 0 times c squared in the denominator. And both of those coefficients can be actually measured experimentally. And when you measure them, you find the stunning results. Those two combinations that appear in the formulas are exactly equal. So the only difference that remains between the formulas is the Lorentz factor. But for the typical velocity of electrons, that factor is practically equal to 1, so it should not be an issue. However, it's still there, it would be nice to understand its role. And to do that, we have to realize that the principle of relativity does not demand that all the forces are the same in all frames of reference. It demands that the consequences of those forces should be the same in all frames. So when the electron is attracted by the wire, we expect that the impact of collision will be the same in both frames. And that impact is dictated by the momentum gained by the electron. So not the forces, but the acquired momenta should be the same in both frames of reference. But the momentum gained by the electron is simply product of the force and the time interval. But the time intervals in both frames are related by a Lorentz factor. So the forces should also be related by Lorentz factor. And they are. Problem solved.
So it sounds crazy, but it seems that the Lorentz contraction at the speed of a snail seems to play absolutely crucial role in the description of all these electromagnetic processes. And which is even more surprising, as we will soon discover, the magnetic field itself can be thought as a relativistic correction to the electric field. And if the speed of light was infinite, who knows, maybe magnetic fields would not even exist. But now let us switch gears to discuss another surprising problem.
Consider an inertial observer watching a fly around his room according to some trajectory x of t. And suppose that there is another inertial observer driving a car with some relative velocity v that observes the very same fly that in his frame of reference moves along a trajectory given by x prime of t prime. From these two trajectories we can compute velocities of the fly observed in both frames of reference, and we will denote those velocities with a small v and v prime. And our next task is to determine the relation between those velocities v and v prime given the relative velocity between the frames capital V. And all we have to do is to use the definition of velocity v prime, which is simply a derivative of x prime over t prime, and substituting the Lorentz transformation formulas for x prime and t prime. As we can see, both denominators cancel out, and if we divide the numerator and denominator by dt, we immediately arrive at the result. We can also check the correctness of the resulting velocity transformation formula by plugging in c instead of small v, which is to test how the speed of light transforms into the new frame of reference. And as expected, we find that the velocity in the new frame of reference is still c. Let us now consider the three-dimensional case of the velocity transformation formula. In this case, the expression that we have obtained characterizes the transformation of the x component of the velocity, and the remaining components of the velocity y and z can be found in the analogous way. For example, the y component is simply a derivative of y prime over t prime, and after substituting the Lorentz transformation and dividing numerator and denominator by dt, we obtain the following result. And the remaining velocity transformation formula for the z component of velocity can be found in the exact same way. And these formulas characterize how a velocity of an object moving in one frame of reference transforms itself into another inertial frame of reference. We will now consider a driver that wants to catch the moving fly and therefore follows the fly with some velocity capital V. And we will investigate how velocity of the fly v prime, observed in the driver's frame of reference, changes as a function of the car's velocity capital V. So we will consider a simple one-dimensional case and try to illustrate the result with a plot. So as we can see, the results are not very surprising. The faster the car moves, the slower the fly escapes, and eventually velocity of the fly drops to zero, and if the car goes even faster, then velocity of the fly becomes negative, eventually tending to minus c. Instead of the fly, we can also consider a ray of light moving with velocity c, and then that velocity will not depend on the car's velocity at all, and our plot will show a flat horizontal line. And now we are in for a treat, because nothing forbids us from considering a superluminal fly, which could represent a superluminally moving laser spot on a wall, or superluminally moving wave of jumping Lego figures. The speed of the car has to be smaller than c, but that constraint does not apply to the small velocity v, which by the way we have just considered to be equal to the speed of light. So let's have a look at the crazy consequences of such a scenario. So let's extend the vertical axis of our plot and consider an object that moves with a superluminal speed. The resulting plot is pretty intriguing. So we find that the faster we chase the object, the faster it escapes. And if you keep increasing velocity of our car, eventually the escaping object will move away infinitely fast. And if we keep moving even faster, then the object will change the direction of motion and will start to move towards us with infinite velocity and gradually approach the velocity of light, but from above. So as we can see, the superluminal objects behave in a very unintuitive way. It feels natural to think that if we chase something, it is easier to catch it, but with superluminal objects, it's a completely different story. So we have analyzed both ends of the spectrum, both super slow and superluminal velocities. And if you felt surprised by today's results, just wait for the next episode, which will be a complete shocker, as we will realize that all this time we have overlooked a fundamentally important property of spacetime. If you don't feel like waiting, just get a copy of my textbook on relativity, upon which the whole course is based. It's called Unusually Special Relativity, the link is in the description. And now I sign off to record the next explosive episode about the... Cheers.